Hello everyone, hope you all are doing well. In this video, we'll discuss the fourth problem of Leetcode BiWeekly Contest 80. It's a hard level problem, the fourth problem of the contest. But honestly, I won't say this is up to the same level. This could have been the third problem of the contest. Uh, so yeah, let's see. The problem name is count subarrays with score less than k. The problem says that the score of an array is defined as the product of its sum and its length. Like for example, suppose this is the given array, then the score of this array will be sum of these elements, which is 15, into the length of the array, that is 5. So the product comes out to be 75. So we are given a positive integer array nums and an integer k. So we need to return the number of non-empty subarrays of nums whose score is strictly less than k. And it says that a subarray is a contiguous sequence of elements within an array. So I would say the approach of this problem is pretty much similar to the second problem of this contest itself, which we discussed in the previous video. Uh, so we will sort of use the same approach uh, with a little bit of difference. Um let's see the examples. So this is the array, and k is equals to 10. So these are the subarrays. So the six subarrays having scores less than 10 are it is 2. So 2 into 1, because the sum is 2 and the length is 1, so the product comes out to be 2. And similarly for all the single elements, the length will be 1, and the value will be the value of that particular number into 1, so it comes out to be same value. And all are less than 10, so these are the five values. And if we consider this subarray, so it's the sum is 3, and 3 into 2, because 2 is the length of the array, so it comes out to be 6. So these are the six subarrays whose values having values less than 10. So these are the six valid subarrays. Similarly, if we look into the second example, so we have three numbers and 5. So the only subarray which is not a valid one is when we take all these three. So the sum will be 3, and the length will be 3, so it will come out to be 9. So rest of the remaining subarrays are valid, so we return 5. So if we look into the constraints, then the length of the array is 10 raised to the power 5, and each value can go up to 10 raised to the power 5, and k can go up to 10 raised to the power 15. That means the product. Now uh, the, the 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 main thing to note here is that it says that number of non-empty subarrays whose score is strictly less than k, we need to return this. The other way to think for this particular value is that if we know how many total subarrays are there, and how many subarrays are there whose value is equal to or greater than this value k, then based on those values we can compute these values, right? Because the sum of subarrays whose value is strictly less than k, and the sum of subarrays number of subarrays whose value is greater than k equals to the total number of subarrays, right? So we will go the other way around, because if we look into the approach, well, let's first try to understand it with the help of a diagram of how to approach it, and then probably you'll be able to understand yourself that why we are taking this approach, right? So this is the array, this is the array, right? This is the array. Suppose the length of the array is n. So how many total subarrays we will have in this case? It will be n into n plus 1 by 2. These are the total subarrays. So okay, we have this particular value, right? Now let's see. Suppose we start with this index. Suppose we start with this index, and we have a subarray. Suppose we consider this particular subarray. And if the score of this particular subarray, that means indices 0, 1 and 2. If the score of this particular subarray is greater than or equal to a particular value, let's assume k in this case. If it is equal to this, if it satisfies this condition, that means if we include more elements here, then those subarrays will also satisfy the condition, because we have all the values are greater than 0. All the values are greater than 0. It is mentioned in the constraints. So if a particular subarray is satisfying the condition, then adding more elements will also satisfy the condition, because in every case we are adding positive values, right? So like for example, suppose we have value x, we add one more value. Suppose we are adding an element having y, right? We are having an element y. Now the total length becomes, now the total length will increase, right? So what we will do, this x was already there. Suppose this x was the sum was this, the length was l. Now what we are doing, this was the length, we are adding one more value. So this value is, suppose in this case, y. Now even if this one is 0, even if this one is 0, then what we are doing, we are at least adding it one more time, because this length becomes length plus 1, because the total value of the subarray will be length plus 1. To simplify this, to simplify this like this has become a complex formula, I totally understand. If we understand with the let's remove it, I'll not make this more complex. We can understand this with the help of a diagram only, so I think no need to go into the mathematical formula probably, because yeah. So what I was saying is that that if a subarray satisfies this condition, then adding more elements will also satisfy that condition, right? Because even if the added value is 0, we will be multiplying this sum with with the increased length. So suppose the initial length was L, adding one more element makes us L plus 1. So that means the value will again be uh, greater than K only. So what we do, we pick up each and every index. So we have total n elements. For each value I, we consider it to be the starting point of the subarrays that we are considering. So suppose we consider this as the starting point, we see what is the first index in the array, which is satisfying this condition. If we know this, then these subarrays will also satisfy this condition, right? So if we know what is the first index, then simply how many subarrays will be there, it will be the total length of the array minus this index. This will give us these values, right? So that means starting from this position, consider this array, consider this array, like from 0 to consider this array, from 0 to consider this array, from 0 to consider this array, 0 to this, 0 to this. So how many subarrays are there? 1 2 3 4 5, right? So, and which is equal to n minus this index. Now if we consider any other index, suppose we consider this one, suppose this is k. No, k we have taken, let's assume we take it j. I think this is a becoming, this is not a very, I know, clean diagram, sorry for that. So if this is j, if this is j, now again we do a binary search, now you must be thinking how we'll do a binary search. I'll tell you how to do that. We'll compute the prefix sum for that. So if we consider j, now we need to see if the starting index of a subarray is j, then which is the first index on the right side which is satisfying this condition, and then for each and every index we'll do this, and we'll add that to our final answer, right? So this is the approach that we'll follow. Now comes the question, how to compute the leftmost index. So the algorithm is good, we are good to go with the algorithm. How, what we can do is that this is the array, this is the subarray, sorry, this is the array, we can compute the prefix sum, of this. Why we will compute the prefix sum? Because suppose, so we discussed that we want to check the first index which satisfied that condition, right? For each and every index I, suppose we are at this index, so and starting index is this, so we need to compute the sum of these elements, right? We need to compute the sum of these elements, and obviously length will be computed in O1, this index minus this index plus 1. So how we can calculate the sum of these values in O1 time? That can be simply done by prefix sum. If we calculate the prefix sum, that means sum of these values minus sum of these values will give us the sum of these values, right? So this will be done in O1 time. So for that we'll be calculating the prefix sum, and we'll be doing a binary search. So for every index this, we check for this particular range, or rather for this range, I would say. Suppose this value itself is greater than k, so considering the boundary conditions, so starting index is this, and considering this particular subarray, do a binary search, check for the prefix sum, that which is the first value which is greater than k, and then we are good to go. So now now since we are done with the algorithm, let's go into the implementation part. So if I show you the code, then again, this is the sum, this is the sum. Why I have taken this? Okay, to compute the prefix sum. Yeah, okay. So this is the length of the array. This is the greatest subarrays, because what we discussed, we need to return the number of subarrays whose value is, whose, or rather score is less than k, but we are computing the other value. That means who are the, which are the subarrays whose value is greater than that value k, right? And this is the prefix sum. We calculate the prefix sum here. We are using a one based indexing to make things simple, because we will see why things will be simpler here. And then for each and every index I, that being the starting index of the subarrays, we do a binary search. So low is equals to I, high is equals to n minus 1, answer index is minus 1. This will tell that whether we were able to find an index or not. And this is the binary search logic. We calculate the midpoint. We calculate the midpoint, we calculate the number of elements, we calculate the difference. Now the difference will be, since we are at mid, and mid is zero based indexing, but we have calculated the prefix sums using one based indexing. So we calculate prefix sum of mid plus 1 minus prefix sum of I, because we need to consider the elements from I plus 1. So here, this is the difference. This, because prefix sum of I will have the sum of values till I minus 1, and we need to calculate the sum till I. So we are good to go. This will give us the sum of the current subarray. We calculate the product, that will be difference into the number of elements. If that is greater than k, that means all the elements on the right side will be eligible. Let's go and check on the left side, because we need to find the leftmost value. So we have made answer equals to mid, because if this is the leftmost value, we are good to go. Else let's check on the left side, and we shrink our sample space. So high becomes mid minus 1, because we want to search on the left hand side. And if this is not true, that means we can find a potential value on the right side. So we make low is equals to mid plus 1. So we keep on doing this, and finally, if answer of index for the current index is not equal to a minus 1, that means we were able to find a valid value. So greater sub arrays will be n minus answer of index, the one we discussed in the diagram. So after this loop, we will be finding the number of sub arrays whose values will be greater than or equal to k, and we need to return the number of subarrays with value strictly less than k. So what we'll do, we'll calculate the total subarrays, and we'll subtract the greater subarrays from this, and we will be good to go. We'll find the answer. Yeah, so this is the accepted solution. And I hope you learned something new from this video. Do support it by giving up a thumbs up, do subscribe to the channel, and if you have any query, then please post that into the comments. I'll try to answer each and every one of them. And see you in the next video. Bye bye, take care.